Started. Okay, welcome. This is a talk, kind of a crazy talk, Petabytes for Peanuts, making sense of ambient data. So kind of what I want to do here is only talk for about a half an hour. Got some friends who'll come up and do some demos of some new things we're doing. And I kind of want you to walk out of here thinking about several things differently. Just sort of the scale of data that we have at our hand now and what to do with it. Thinking about data, programming against data that is as events, writing queries against event streams. Maybe Eric's going to show us how to write a query against sort of how to process the mouse events or something, which he's done before. So it's a couple different things, and I want to leave at least 20 minutes for Q&A. And that's the part where it's only as good as you make it. So I would hope for some vigorous Q&A, because there's actually a lot of confusion and strong emotions around some of the large data stuff that's happening out there today. So with that, key takeaways, massive shifts in how we process data. And I want to talk about some of the forces behind that. Just amazing data volumes. At Microsoft, we have systems that process petabytes of data in small bounded time. And it's actually remaking how we discover things. There's a tremendous amount of things happening in the bioinformatics, pharma, other scientific discovery that we'll touch on as well. Reducing latency and impedance, we'll talk a little bit about that. From writing programs to writing queries, we'll touch on that a little bit. And if someone wants to get a little fun, we can have a discussion on what's this anti-SQL stuff all about, because I'm kind of a SQL guy myself. So just to start it off, I want to throw some wild numbers. I was doing a talk a couple of years ago in India, and this is a picture I took in India, and it was on my digital camera, which produced an image that was 10 megabytes in size. And okay, so I got the gray hairs. I've been doing this for 25 years. So the first machine I got at work was an IBM PC XT with a whopping 10 megabyte hard drive. Okay, it's a hard drive. So think of this thing. You could put one picture on it out of my camera now. So in 1982, the storage cost is roughly $2,000 to store the picture. Transfer time at 1,200 bits per second, which was about the best you could do with wide area network at that point, about a day. Okay? And this is one picture out of my camera now. And I rolled it forward to 1997. Storage cost, in terms of just the raw hard drive space, was about $1 at that point. Transfer time at 56 kilobits a second, about a half an hour. And I redid the numbers earlier this year, and at that point it was about 1/10 of a cent to store the image. Transfer time on sort of a modern broadband connection, roughly 8 seconds. So the point here is that people get hung up on, it's a little bit faster, it's a little bit faster. But there are times in which it completely changes the experience or enables things. And this is what's happening in the large with some of the data that we have at hand now. We'll talk about that in the next few slides. So with respect to ambient data, I just went out and did a couple searches and tried to find some interesting data volumes. So this thing I found today, 2 trillion minutes on cell phones in the US in 2007, okay? And that's from clicks.com. And what I did is I figured out, if they were all GSM, I found a bit rate for GSM encoding. And 1.6 billion text messages per day, and this was December 2007. I suspect it's much larger. But if you think about the text message traffic now, we're talking about 160 gigabytes a day at that point, 58 terabytes a year. Voice traffic, based upon the GSM encoding rate I found, is roughly 200 petabytes a year for all of the US. So that's sort of what we've got flying around there right now in ambient data. But what was the old world like? The data volumes were constrained by human typing speed. I mean, we used to pay people to type information in a digital form so we could feed it to the mainframe. And the application and the data formed a closed system. And so we basically typed it in, and it came back out. And every one of these systems was a silo. So I found this other little factoid. They say for a very good and competent keystroke operator, if you can still find one, it says keystrokes, but it should be strokes, 10K keystrokes an hour. So I assumed if had roughly 200 million people of typing age in the US, typing 8 hours a day, they could generate roughly 6 petabytes of data a year. Or 2 terabytes an hour. Now hold that 2 terabytes an hour in your head for a second, because we're going to get to some other things. So here's the new world, okay? Now, this is the old new world, I should say. If you go back to the early 90s, when we started to get some fairly large data warehouses, many of the high-end, the sort of benchmark in size data warehouses were call detail records from the phone system. They were getting the data out of the switches and then building data warehouses. So it was a transition from human input to automated data that got us up into this world of terabytes at that point. So in the old world, we had some available data. We thought of the questions we want to ask of that data up front. We designed a schema that corresponded to that. We designed the ETL flow, and then we had data warehousing nirvana. Life was great, right? Well, here's what's happened along the way. The available data has exploded. And now, quite often, we have to ask ourselves, what data do we throw out? I was talking to a national health service for another country some time ago, and we got into a discussion around the challenges they faced in terms of what 90% of the data that they had at hand did they have to throw out to get, build a data warehouse around this thing. And they could get their hands onto things that would be incredibly useful, like GPS telemetry from ambulances and such. But they had no way to really reason about how to get it into a data warehouse and couldn't really imagine even getting it all in there. So the other challenge we have with this is, what do we do if we have a new question? So at Microsoft, we had this problem. We actually have, as you can imagine, some significant volumes of data coming out of our live properties. And we did a traditional data warehouse and wound up, at some point throwing out a lot of the data. Challenge we had is, 6 months later, we'd have a new question, and we couldn't even pose it because the data that we needed to answer the question had long since been thrown out as part of this flow. So now we're in this crazy new world of abundant data, and this is something we're doing at Microsoft as well. So the idea is you don't throw anything out, nor do you bring it into a traditional relational data warehouse. And when there's a new question to answer, you run I'm going to put this in quotes, a query over the data. And the thing I'm kind of getting at right here is sort of the whole Hadoop, MapReduce phenomenon going on, which Microsoft has its own technology in that space. And what's happening is many times what people will do is they'll run this large job over literally petabyte scale data volumes and produce a reduced set of data that they'll use for subsequent analysis. But the fact that you haven't thrown anything out allows you to pretty much ask any question at any point, run the job for a couple of hours, and produce the data you need to do the analysis. Now here's I got to sort of obfuscate this a little bit. There was a point where we had, let's call it some activity that was tainting our data. Someone's laughing. I think I don't know where I'm going. Was tainting our data in our own collection. And what we were able to do, so what we did is we keep producing this reduced stream that actually forms the basis for the business metrics, the more traditional data warehousing. But we had something upstream, I'll say, that was tainting the results. And what we were able to do is understand what was perturbing the results, reprocess that data effectively with a filter that took that out, such that we could get clean data with respect to what the business was actually doing. Now, that's not something we could do unless we were in this new world and operating on the data in this way. There's also another sort of path along this, which is the path I call algorithmic processing. And this is just stunning with respect to what's happening in the scientific world. And I'll actually give you a couple of examples and a pointer to read here in a second. So the whole scientific method, I mean, this is incredibly profound. The whole scientific method around coming up with a hypothesis, a theory, and then testing it is being turned on its head, where sometimes correlation is enough without even understanding causality. If you can run large-scale data mining over this and find statistically significant correlations, it either represents a place to start looking, or it represents enough that you can, in fact, take advantage of it. And this is just mind-altering. And just to get into that another sort of insane data volume, one of the experiments that they're running on the Large Hadron Collider records a terabyte of data a second. So we talked about all of the typing age people in the US typing at an incredible rate for an hour. They could produce 2 terabytes of data. This thing is producing a terabyte of data a second. Burton, you know if any system is doing more than that?
Yeah, there's a confocal microscopy in biology, which takes movies of cells at the
And what's the data volume?
It's petabyte a day kind of volume.
Petabyte a day kind of volume out of this other system in the molecular biology space.
Yeah, yeah. But
So,
50 terabytes a second.
yeah,
Yeah,
big numbers. So here's an interesting read. It's sort of a layman's take on this, but it's from Wired Magazine, The Petabyte Age, because more isn't more is different. It's actually kind of a fascinating read, and I've got the link here, and you can get your hands on the slides and actually take a peek at that. Okay, so there's one other thing that I want to talk about, and this is, I kind of switched the order on these so we could get these folks up to do a brief little demo. Another thing that we see happening in these extreme scale sorts of things are people doing analytics over the data as it lies. So I'll construct an example to sort of make this flow real. So imagine you have financial, if you will, credit card transactions and such. And you're just recording them on disk, just however they're landing there. And what you're trying to do is actually run mining algorithms over this data to find sort of fraud activity and signatures of fraud. So once you've actually identified them, and I'll kind of walk through the flow here. So my point is, there's a lot of activity and talk around stream processing of data. In reality, there's this duality. Quite often, these streams of data hit disk, and you can do historical analysis over them as well, and they all fit together in one interesting cycle. So in this particular case, we say the event stream is both stored and processed. We run analysis over these and produce correlation models or other sorts of models. So in this case that we're making up, we'll find out signatures, if you will, of sort of fraud. Then we'll take that model that we've built as a result of that analysis, place it into an event processing engine to be able to do real-time detection and alerts. Now this works for fraud, it works for intrusion detection, it works for doing, if you will, machine learning over anomaly detection for large-scale systems. We're doing some work there as well. In fact, we had, and I'll again obfuscate this a little bit, we had someone in Microsoft Research who had done some work to identify signatures of online systems before they went bad. So the system was going to get to the point where it got in a wedge state. And without having any sort of theory, he unwound things to try to find statistically significant indicators that would correlate with the system ultimately failing. And it was something on the order of like 70% of the cases we just threw at this thing, he was able to determine a sort of initial cause up to 30 minutes before the system got in the state where it actually reported that it was in bad health. And so there's some amazing things that we can do here. So with that, what I'd like to do, invite Roman up from the Stream Insight team to give us a little bit of a demo here. And I'm actually, so one of my dirty secrets is I have a degree in robotics. And so anytime we get any hardware up here next to the machine that we're doing stuff with, I think it's pretty cool. So what are you going to show us?
Thanks, Dave. I'm going to show you a little demo for an example from the power utility space. Think about power meters, measure consumption, power consumption in households. So what I have here is one power meter. Imagine I'm the utility provider. I have my own power meter. And the power meter measures the consumption of the device that's currently plugged into it, which in this case is just my laptop. So what I'm measuring here is the power consumption of my laptop. The thing about this meter is it streams out the power reading through a USB interface, and I can read that through a serial protocol in my stream processing engine. So what I have in my demo here, and you already see Visual Studio, is a Stream Insight application, a Microsoft Stream Insight application that reads the power consumption data from this device, streams it into a standing query that I specified as part of my application in a declarative language, and then streams the result of that query into the output of my application, which in this case is a dashboard window that just displays the events as they are streamed out of the engine. So what I'm going to show you is how the events are processed in terms of a standing query, how to specify a query that operates on the power readings that were read from this device, transformed into the Stream Insight event format, and then streamed into the engine and then into the output adapter. So what you see here is the important part are the
So we should really, Stream Insight is a stream processing system that we're developing. It's in CTP right now, correct?
Yeah, it's pre-release. It's a public beta. It's available to download, and it will release together with SQL Server 2008 R2 next year. We have our public beta out since about half a year, so everybody's invited to try it out. It's a platform. It's an SDK, basically. You download an MSI, you install that, you get a bunch of DLLs on your machine, and you write your application against that API. So you see that actually here in Visual Studio that my application references the DLLs that are provided by the Stream Insight release by the MSI that you install on your machine. And this provides a couple of interfaces. First of all, to write the adapters, to actually be able to convert the proprietary event format into Stream Insight events. And it also enables you to write queries on top of that and to put your application together in terms of adapters bound to specific queries and then starting and stopping those queries.
So I'm going to, see, this is my way. I just keep interrupting you, so that's okay. You'll do fine. Okay. One of the other things I bet you can do is, we talked about the historical analysis. So you could actually write an input adapter that takes stuff off of disk, runs it through the same thing. So this is showing live streaming of events, but we could also do it from disk for historical analysis.
That's one of the important notions of the system, that the specification of the query logic is independent of the actual event source or sink. So you can take the same query, bind it to an adapter that streams real events, real-time events like this one. You can take the same query and bind it to an adapter that is reading historical events from a database, for instance. And it would operate on the historical time series.
Cool.
Okay, so in this case, what you see here is a query. Our query specification language is LINQ, so it's closely related to SQL. It has all the relational notions, but we added the temporal behavior to the query language, so you're able to specify temporal properties in terms of windows, aggregations over windows, modifications of timestamps, everything that is important in the real-time event processing.
So in fact, that's an interesting thing, because that's something we worked with Microsoft Research on, because most systems are event-based, and we actually have a temporal algebra around this as well,
yes,
right?
It's purely declarative. There's a well-defined algebra, and our link surface, the way we specify our link surface, has a well-defined semantical mapping from that to our temporal algebra. Okay, so this example is a very simple query. It's basically a pass-through query. It takes each event out of the input stream and generates an output event based on the input stream event fields. In this case, I have an event field ID, which is kind of the meter ID. I have only one meter, so I will always get the same result for the ID field. And then I have an int W field, which specifies the wattage reading, which in this case is just an integer reading. That's the way the meter works. It measures the power consumption in tens of watts. So what I'm doing here is I'm dividing that by 10 and converting that into a double to get the actual real wattage. Let's see. Okay, so what you see is for each event that is coming into my engine, I'm producing an output event. The property of this specific device is to produce about 20 to 30 events per second, and this is my data rate that you see here as well. So let's keep the last 20 events and freeze that output for a second. This is just behavior of the output window. This is not really the engine that's stopping. So you see that I get a bunch of events per second. They're mostly all the same because the power consumption doesn't change that quickly here, and I always get the same ID. Okay. Now it changed a little bit, and if you look at the wattage readings, they are not really smooth. They are changing with watts or tens of watts, but it's not really a smooth curve. So let's say I would like to change the data rate. I would like to reduce the data rate here. I'm not interested in 50 events per second. I would actually only like to see one event per second. But this is not supposed to be any event, but it's supposed to be the aggregation of all the events within a second. So it's a typical streaming example where I want to aggregate the input data and resample it. I want to reduce the data rate. Okay, so how does that look like in terms of the query? So first of all, I'm applying a window on that input stream. In this case, I'm applying a tumbling window. Tumbling window is a window that tumbles along the timeline, meaning that the new window starts whenever the old window ends. So it's gapless and non-overlapping window. And you see IntelliSense picks up our extension methods. So I get all the streaming functionality that we use to extend LINQ in Visual Studio. And I'm specifying a time span of, say, 1 second. And now I'm aggregating. So I specify, okay, let's call that window, because that's what it is. Okay, I have my average is the window, and now the average function on top of the window. It's again an aggregation that Stream Insight provides on top of that input. Wouldn't be a demo if that would work, right? Okay, so you see the different behavior now. We reduce the data rate. It's exactly 1 event per second. And it's the aggregation over that whole second. So you see that for each second, we generate exactly 1 event. We change the behavior. This is still a simple example in terms of number of inputs. I still operate against one single meter. So the typical use case would be to have many of those meters in my input stream, right? I have many meters, and I would like to apply the aggregation operation on each of the meters separately. So that means I have to basically partition the stream by a specific input property. In this case, and I can't really run this because I only have 1 meter, but imagine I have many meters and the ID field of each meter is different. So that means I would actually like to group by the ID field and then apply the aggregation on each of those partitions separately. So what I would do, and I just show that here in Link, is I would take the input events from my stream and now specify grouping. And I will see that again, IntelliSense gives me all the fields of my events, and somewhere there's my ID. There it is. So I group my input stream by ID into, say, each group. And that's, so far, that's plain link functionality, actually. And now I can see from each of those, and again, I'm using the window if I want. So I take each group. Now I can I again apply the window here, meaning that I aggregate each group separately. And this looks the same as before. So I still have my window with my aggregation on a specific field of my event stream, W. So that's all I would have to do to partition my stream by an input field. And that's typical streaming pattern. First partition something, and then apply an operation on each partition separately.
Thanks. Awesome.
Thank you.
Very good, Norman. So the cool thing there is it's all Link, right? And we have a tremendous amount of interest in this. And we'll tie that back into sort of the large-scale processing of stuff on disk here in a second. So thank you much. Okay, so let's talk a little bit about the extreme scale data processing, and I'll sort of do a little op-ed here where I think there's some confusion out in the market right now. So the traditional data warehouse, we talked about this, where the majority of the data is filtered or discarded for some of these extreme scale sorts of things. In today's world, we have these non-traditional sources, things getting written to disk in whatever form it was produced in. Now here's where it starts to get interesting, is that some of those non-traditional forces could be in formats that are not sort of amenable to putting in a relational database. So you could imagine storing copies of the web with HTML and having pages and such. So then how do you process that? Well, you could imagine, and we talked here in the Stream Insight case of having an input adapter. But let's say for a particular task, you wanted to do a link analysis and look over all of the hrefs in this HTML to figure out how many of them were referring within the domain or outside the domain and such. So you could just produce an input adapter that would produce a tuple stream that then we could process using the standard relational sorts of things that we've been using for decades. And the work that's happened in the relational database space to do parallel query processing and optimization of these is still applicable in this space. So this is where people start to get disconnected. This is where the functional programming guys like Eric would tell us that we just need a functional programming language over this. And this is where the database guys say that, no, this just belongs in the database. and they haven't really come together. But Eric's actually been working in the database group for a couple of years, so he's actually reformed a bit and is now trying to marry his functional programming roots with the database. So he'll come up and show us that a bit. But there's a tremendous amount of confusion and anxiety around. That's where a lot of this anti-SQL movement's coming from in terms of the processing in the large. And my point is, much of the technology that we've developed over decades in parallel data processing still applies above where the data is stored. And so there's an interesting thing that's played out here. If you think about MapReduce, if you think about some of the early efforts to go do this, they started, I think from the, Eric, you can sort of fill in some gaps, started from the functional programming community, and then they realized, well, it's kind of hard because they have to write programs all the time. So they tried to up-level to make it more query-like. So everyone who had one of these functional programming scaled-out data processing systems, every one of them developed sort of an intermediate language. So I think Google has a thing called Sawzall. We have one called Scope. The Yahoo guys have one called Pig, I think it is. So the thing was, how do we up-level that? And I think it's just sort of one step along a path where we'll start to use more and more of the traditional technologies we've developed and bring these things together like this. It's kind of funny right now because these worlds, they're kind of just starting to acknowledge each other. So I think this is actually a pretty interesting thing happening. So with that, we'll bring Eric up, and Eric's going to show some wild stuff. He's taught Link to do lots of crazy things.
Yes.
And you got a microphone here too.
Yes, yes. I was looking for my mouse because one of the things that, what Dave said in the beginning, making lots of data, so that's kind of what we're trying to do, is making everything look like a database.
That's what you get from hanging out with the database guys for 5 years.
Exactly. So look at this. There's my mouse. So do you know that this is a database? Good. This is a database that has mouse move events and button click events. It's just like this meter, really. This is just a database, and it's not stored in this. Well, I don't know. Maybe the mouse moves are stored in this. You don't know. They just come out. So let's look here. I'm going to show you two things. One, let me go here. Is when Dave mentioned MapReduce. So let me kind of put this thing as my startup project. And so we have something called Dryad Link. Dryad Link is an implementation of MapReduce style thing that where you can write link queries and they kind of run in parallel. What I show here is kind of a little poor man's version of Dryad Link or of MapReduce to show you how easy it is to make your own link providers to do that. As Dave said, link to everything. The whole point of link, something is kind of creating some sound events here. The nice thing about link is that it allows you to kind of put in any data source underneath link that you want. So, for example, you saw the Stream Insight guys. They didn't have to do any new language design. They just took C# and they implemented their link operators on top of their engine, and you program it just in C# and you get all the kind of IntelliSense and everything from there. So here I have a super simple example. This is one of the examples that the Google guys have when they talk about MapReduce. This takes a file with words, and then if the word is not empty, it turns the word into lowercase and it groups by each word, and then it just gives each word plus the count of the word. So this is like going through a document and finds all the frequencies of all the words, and then I order by the decreasing count, and then I just turn them into an array. So now let's go here and go into these sequence operators, and I'll put a breakpoint here just to show you how crazy this is. And I will run it.
But you're looking behind the scenes right now.
You're looking behind the scenes. I really want to show you how easy. Oh, look at this. That's really quick. So what happened is I wrote this query that was turned into all these sequence operators here. And here I have my own special implementation. You don't have to understand how this works. But I've defined all the sequence operators, select, where, all the query operators. And now I'm inside this implementation. And at this point where the breakpoint hits, I now recreate that query internally in order to run it in parallel. So what I've done is I've kind of, it's like a Russian doll. I've kind of put myself inside the query, and now when the query executes, I get a representation of the query, and I can now use that to build little subqueries that I can run in parallel. And so it's
So you specified one top-level query.
You start with one top-level query. You're putting yourself inside the query operators. So the query kind of folds inside of you, and now you have that query. And now I can say, hey, here's the query. Now I want to run it. This part here, this part here, this part there.
In fact, you could have these books spread over 1,000 different machines.
Yep.
And be able to redistribute at this point. But someone would still, they wouldn't have to concern themselves with how to partition the query across the...
Exactly. So here you see that I've reproduced my query, and then here I'm mapping this over a number of files, and then I repartition them, and then I kind of return the results back to you. So let's just run it and see that it really does something. So now look at the results here, and you see, as expected, the word "the" is it has the highest frequency. It's interesting. Maybe you can find which book this is. It's from a Russian writer. It's obvious, Tolstoy. Good. Here, look at this. This is like event processing here. So this is an example where that shows how easy it is to implement your own link provider, and in this case to do your own MapReduce style thing. And this you can build this on whatever fabric or computational fabric that you have. My next example is what Dave said is I'm doing queries over distributed programs. So now I need to set my startup project to this one. There we go. And then it's this one. And let's run this first, and then I'll show you what it does. Hopefully my network connection works. So what I'm doing here is I'm taking a input from this web page, if it's loading.
Google is undefined.
Google is undefined. So now let's...
Yeah, there we go. That's appropriate for today.
Only at a Microsoft conference is Google undefined.
Yes. So maybe I need to switch to my other demo. The network connection is... let me just see if that's up. That's always... It was working before I came here, but somehow...
All right, let's go on. And
let's go on. I won't run the demo.
I'm kind of anxious of looking at that mouse. I want to see
exactly. You want to see the mouse. Like, okay, let me show you. I won't run the demo. I will show you here. There we go. So here is the demo, the code. Here we go. So this one doesn't take the mouse. It takes the keyboard input. So if you say here from text in input, every time you type in a character on the keyboard, that will, if I show here, this has type IObservable of string. So it's very similar to the Stream Insight demo where out of this thing came a event stream of meter readings. In this case, I look at my input and out comes a stream of strings. And in this case, we do that with observable. Now then what we do, and this is something that is special for this case, that looks here very daunting. What we want to do is we want to send off 3 requests to a web server. So in this case, I want to send things to Bing. So I want to do a Bing translation. So I'm sending the same text that I get here from the input. I'm sending that to the translation here to translate it from English to Dutch, from English to French, and from English to Spanish. And then what I want to do is I want to wait until 2 out of 3 translations have come back. So this is kind of a similar like complex event processing where I have 3 event streams coming in, and I want to now synchronize on 2 of them. And the way I do that is it's really a little bit like Outlook rules. When an email comes in, you can write a rule saying, you know, if it's from this person, you put it in that outbox. If it's from that subject, you put it there. You can write exactly the same rules here over incoming streams of data. And in this case, I say, if there's a result from Dutch and French, well, then I create a new result that has Dutch and French, but no Spanish. And if I get French and Spanish, well, then I get no Dutch and French and Spanish, etc. And here, the last thing is also interesting here is that I want to cancel this web request as soon as the next input event arrives. So, because if I start typing again, I don't want to do another, I want to kill the request that's in flight, and then I just return the results here. So here's what you see is that I've written here an Ajax-style application that meshes up different web services and takes the event streams, like from your mouse or from your keyboard input, and turns that into event streams that you can query using Link. And again, just like the other example, this is just another implementation of the Link operators, just like the Stream Insight guys. Everybody can build their own Link implementation. And so we can turn anything into queries. Everything is
I'm
data.
just sitting here thinking about all the database guys in the room. We've been trying to teach people how to go from sort of imperative loops to queries for decades, and now you're just going to take them one step further. You turn the Ajax programmers into the same.
Yes, look, if I'm in a database group, I have to turn everything into queries, right?
Good.
But yeah, so, and again, so if you want to kind of learn more about the Link stuff, there's plenty of information on the web, and it's really fun to implement your own Link providers. It's really cool.
You're not going to show us the mouse?
I can show you the mouse.
Just real quickly.
Real quick.
So a 1-minute mouse.
Okay, sure. Let me show you the mouse, Dave. I'll show you the mouse right here. Come on. There we go.
So this is using the reactive framework, which we've just sort of posted on Live Labs recently?
We posted this on Live Labs. So this is a pre-recorded demo. So what I do here is I'm having an input adapter, again, like the Stream Insight. I'm adapting the mouse moves into an event stream. And now what you see here is I write queries that take the mouse down into an event stream, the mouse moves into an event stream, and the mouse ups. And then here you see a little query that is highlighting now, that is turning these event streams into a stream of drag and drop events. And now I'm joining all the moves to kind of get the positions, the difference in the positions of the mouse moves. And then I'll just, whenever I get the difference in the position, I will update the position of the control to modify that. So here you see this is the mouse move. So now I'm dragging this mouse, and this is a query. Every time I'm moving the mouse, an event stream is generated. I'm querying that, I'm joining these streams, and then I'm pushing back the events to the UI to update the mouse position. So GUI programming is just queries. Everything is queries. Everything is data.
I'm glad we have you in the
Yes.
team. You're going to keep this is the full employment act
Yes.
for database guys.
Of course. And, you know, we can make everything into a database.
Okay. Thanks, Eric. That's cool stuff. All right, so the idea here was just sort of stretch people's imagination with respect to the scale of data that we're processing, the role of traditional databases, what we have going in terms of extreme data processing, where it lands, and this whole notion of how to think about events, whether they come from disk, whether they come real time, as sort of unifying them, and then using Link as a way of sort of querying across all of these sorts of things. So with that, just as a sort of little thing to lubricate the brain, let's take some questions. We'll do hard questions, easy questions. We'll call on some of the other. And if you want to use the mic, otherwise I'll repeat the question. You line up at the mic. Let's do some interesting questions. Yeah, use the mic. We'll bring the mic in. And we don't want easy questions.
Okay, this is a hard one.
Okay.
I just have a question for, I think, sorry, I'm hearing my voice.
I'll repeat the question. So the question is, Stream Insight, are you thinking about using it for any sort of real-time search engine sort of stuff? If you can either grab, if you want to come up here, just grab this mic right here. Oh, yeah, yours might still work since you're still wired up. Can you bring him up? Oh, yeah, he'll feed back. All right, so either hop up here or...
So, yes. Yes, good question. Clickstream analysis is one of the verticals we're looking into regarding real-time event processing, basically taking the log of all the clicks of a website, and that could as well be, search keywords, URLs that were submitted to the web server containing the search keywords, and then processing that stream and do something with that. That could be, adjusting the ad placement targeted to that user based on some behavior of that usage, or maybe adjusting the navigational structure of the website based on the pattern that that specific user showed over a period of time. And it could as well be some Twitter application where you are doing something in real time based on Twitter keywords, triggering something based on events, on pattern of events. That's one of the applications of Stream Insight queries is pattern detection. You would like to figure out whether some event A happened within X time units after some event B, and then trigger some action on top of that.
Okay. So we have any sample applications like that?
We do have samples, not specifically for click streams. We have samples as part of our release, which are like self-contained smaller samples. They are not really interfacing IIS or some kind of web server log functionality.
Yeah, mention your talk tomorrow.
Yes. Oh, sure. Yes. So anyway, we have our talk tomorrow. We have actually 2 presentations tomorrow. We will talk about that vertical and other application domains. There is one talk at 10 a.m. tomorrow. That's a level 200. And then there is one at 3 p.m. That's a level 400 talk. So 2 Stream Insight talks tomorrow for everybody who's interested. And again, back to the question, we don't have such sophisticated samples that have a lot of moving parts. Our samples are small, self-contained projects in the form of a Visual Studio solution. But that's part of the MSI that you can download already.
Okay, good, thanks. Another question?
Okay, this one's, yeah, it is kind of weird to hear your own voice. It's kind of a helicopter sound back here, you get a really good echo. Feel like I'm in a big mansion. But I'm interested in how I could use this technology or a similar technology to solve distributed write log replicated SQL Server problems. Specifically, a lot of the kind of data that we collect in a stream or from users on a website doesn't need to be transactional Visa-like data that goes click, click, and it all has to fall in sync. And SQL Server's paradigm today is kind of thinking like that the data has to write now, and it has to globally write now, and it has to be in the logs now. When, collecting Facebook-like pictures, that isn't true. Like if it doesn't get written to the SQL Server in France for another 4 or 5 hours, that's okay. So is there some kind of process here to solve a lazy write on the SQL Server, specifically so that when you have multiple large sites that you can write the data into the SQL Server and then it'll lazily write it afterwards? And I have another question after this one. But
okay, so that specific sort of scenario comes up quite often. And the idea is you want to be able to commit quickly locally and then have things replicated. And people typically use transactional replication as a way to do that, to achieve sort of the scale out in geographic distribution. There are other things that we've developed, change data capture that shipped in SQL Server 2008. We can actually quickly locate things that have changed and then pull them out and move them over somewhere else as well. So there's several things sort of in the standard SQL Server product that can help in that space.
Yeah, so the second question is it'd be really handy to be able to turn the transaction log off. Set transaction, no, I really mean I don't need it, I don't care. If this data dies, I don't really give a shit. And if you could just set that command in there somewhere, that'd be really great, because one of the problems today, as you all know, is the transaction log eventually backs up the problem. So what you just said works in somebody's theory, I guess, but it certainly doesn't work in mine, because the transaction log itself is the problem. And so you need some hard way to really tell the SQL Server, no, I don't even mean log one row. Just start taking millions of rows of data and don't make the write logs, right now the write log is a very serious problem. And the more SQL servers that you add, the problem just multiplies, right? So when you've got 3 SQL servers replicating, it doesn't matter how fast you can read out of it. The write log is 3 times the SQL servers.
I got it.
Right.
So, well, there's a couple of things going on there. One, a lot of people ask us for, turning off transactional support, turn off, right into the log. I actually worked on a product before coming to Microsoft that did exactly that. The problem was as follows, is that people just think of like, I don't care if I don't get this record in the database. But in reality, the log is also controlling all sorts of other physical structures as well. So if we're putting stuff in, we're not recording the data, but we're splitting a B tree and we failed there, then the problem people had with this system, that we actually had exactly that, if you will, feature in it, was that they'd have some data and they'd go incrementally load some other stuff and they'd fail in the middle and lose the entire table because it became physically corrupt. And then they'd scratch their head and get mad at us because they thought, well, I turn off the transaction log, just means I'm not going to get the records I stuck in there. So that's part of the challenge, separating those two things. The other thing that's interesting is that for most people, the transaction log latency typically is not that much of a challenge. I mean, it's volume-wise. We do have logging and recovery modes in SQL servers, that reduce the volume of data and maintain the physical consistency, and then you can catch up with an incremental backup. So there's some things, and that's more like an offline kind of question, I think.
Yeah, I think, though, that when you start talking about putting a petabyte of data into a SQL server, that realistically, when you start talking about bringing them into 10 SQL servers distributed, the transaction log is starting to become a huge problem. Like right now, I have planned, first of all, I have planned that you're going to fix it. That you're going to come up with some kind of real lazy write system that works. So.
Basim's smiling up here because he was involved in a lot of this stuff. Tell you what, let's have you chat with Basim offline here in a few minutes, because I think this is something that's a little bit more specific to your case. Okay.
Fair enough.
Let someone else. Yeah. But we do have folks who can answer it in the room. Yeah. Next.
My question targets the link theme. I mean, we love link, and link is a great thing, but we are developing applications in the SaaS area. So our clients can change the data model fundamentally themselves. They write a lot of scripts, and with these scripts, they change the behavior and business logic and workflow of the stuff. The problem with link is that I have to have a kind of fixed type system, and I have to compile this stuff, but we really have to program against an unknown data model, because we don't know the data model when we compile our stuff, and it's quite hard to handle this with link, and so we end up writing our own little programming language and building an abstract syntax tree and compiling it to SQL again, and sometimes also into expression trees to get. It's quite hard. So my question is there a kind of making link more dynamic, using it in a dynamic way, in a dynamic language?
That's a great question. I mean, so one of the advantages of link is reducing the impedance between what you're thinking about in code as a query and the rest of the environment. One of the challenges, with SQL itself being such a dynamic environment, and the way I usually bring this home is like, okay, what does star mean in select star, when someone can just alter things underneath the covers? So there is sort of that tension, and I'll let Eric sort of respond to that if he wants to.
Yeah, so the thing is, in principle, link can be completely dynamic. I think probably if you say that you're querying against a data model where the data model is not known, there the problem is not so much with link, but with C#. because in C# you cannot do that. But fortunately in C# 4.0 there's now support for dynamic, and so you can have an IEnumerable of dynamic or an IQueryable of dynamic, and then you can just use the dynamic language support to query over the elements in your stream. So the other question is if you want to really build queries dynamically, that's kind of the other dynamism. But if I understand your question correctly, that's not the problem that you're facing. But yes, dealing with things where you don't know the static type of your data, I believe that with C# 4.0 dynamic, or even in VB with late binding, you can deal with that. And on the other approach that you can take is you can go to a universal data model where say you have something like JSON or XML, you can query over that too. But the query part, I think, is completely orthogonal to the shape of the data that's in your query. It's like IEnumerable or IQueryable of something, and that something can be static or dynamic. So we can talk about that if you want. For the dynamic queries, now that was a question I was trying to push under the carpet. So for the dynamic queries,
There are other implementations, as you know. We have tried Esper, for instance, and they have an EPL, event programming language, which is string-based. It's a bit better. So I love Link also, but how do you solve this?
okay. So
Make
again,
sure you repeat the question.
Yes, I can repeat the question.
Because I got to catch a plane.
Okay,
and
sure.
Those guys that called were supposed
Sure.
to pick me up.
Okay. The question was, can you deal with if your query is dynamic? And again, that is not a fundamental problem. The only thing is that if you want to have language support, if you want to write nice link queries in the sense like you want to write from, where, select, and so on, in that case, the query has to be static because it's the compiler that takes that syntax and turns that into expression trees or calls of the sequence operators. But if you can create, but these things are created at runtime. So at compile time, it creates calls to construct these trees at runtime. So you get slightly uglier syntax, but you can easily construct these query trees at runtime. Another way that you can do, and there's a sample about that, is you can have a little string language that at runtime you parse and compile to expression trees. So even if you want to do queries dynamically, you can do that. But the downside is that, yes, it doesn't look as nice.
Maybe I can have a follow-up on that. What you described currently is exactly what we are doing now, but we offer our customers a way to write scripts with the DLR, all this dynamic stuff. And now it's not very beautiful. It would be really great to have kind of link in a dynamic language, just as Iron Python or things like that. Do you think that's possible anyway in the future?
Very good question. I would say C# is now a dynamic language because the C# dynamic feature uses the DLR, exactly the same DLR that's used by Iron Python. But, sorry? It's yes. Yeah, but just like Iron Python, it uses the same thing under the covers to do late binding.
Yeah, but I have to compile the C#. C# is not...
So the thing is you want to have a REPL loop and things like that. Yes, I want that too.
Stay tuned. All right, anyone have a question or challenge relative to the scale of data, whether it belongs in a database or not? Or, yep, here's someone over here who's got a question.
So the question is about making sense of the data later on. Like Netflix has the problem of recommendations.
Yep.
So, what is Microsoft doing to help with that kind of programming models or something like that,
So the question is, I'll put it up as the mining in the large, right? And I think the best answer right now is that Microsoft is doing an awful lot of that itself and is learning rapidly for itself. And so the question is then, how do we bring it to market? We have a data mining add-in for SQL, but that's sort of the data mining in a different flavor. And so we've had discussions on that. I actually think that what we found with Stream Insight is very good synergy with some things we're doing internally in our services. So I would say that I look at our, some folks from MSR and such, that is something that we're looking to bring forward in some products going forward. There are no immediate plans for it, but I understand how, I believe, I'll say it this way, that will become commercially viable. Today you need the set of PhDs in the corner to pull it off. And I think that that will become commercially viable here in the next couple of years.
Thank you.
Yeah.
My question is, in terms of the database, I'm using machine learning tools which don't like data in relational formats. And so I find myself doing ETL outside of SQL Server to put it into something that SPSS or SAS or Clementine can happily consume. And as the databases get bigger, that's nice, but the tools that consume it are still looking for a different data format or a flat format. And are the queries, are these stream queries going to be able to service those animals, or do we still have to put it into the database out of the stream in the sort of meta query and then feed them to the other animal?
That's a great question. So in the picture that I drew where we could have petabytes of data spread out amongst the pattern that's emerging is what people will do is run one of these scaled, whether it's our Dryad, Link, MapReduce, sort of Hadoop, and they'll produce a reduced set of data that you'll use for your analysis. What we found is that in many cases, people want to have a reduced set of data they put in a SQL Server relational database. Quite often, they want to put it into an analysis services cube. They could also put it into a flat file. It could be consumed over there. So that general pattern we see happening an awful lot. And I think it's just a matter of that large step reduces and produces a more manageable data volume in the format that you need for whatever tool is downstream. So it's just part of the data and information flow.
So you're using the stream to sort of deal with the fact that you can't deal with the volume of data you have as a single query. You have to stream over it and look for trends?
Yeah, actually, when I say stream, we're using the concept of, if you will, the stream processing over data that has been stored on disk in whatever form it was produced in. So it's used for a variety of things. There's the input adapting, which I think a good example is, say I go from if you will, an item that contains HTML, and then from that I might want to count the number of characters in each page. I might want to produce a stream that has the hrefs and some associated stuff. So there's adapting to whatever is there. There's doing the subsequent processing. So if you think of Eric's example, where he was going across, it could have been distributed across hundreds of machines, producing the top word occurrences. And then from there, you can emit the data in whatever form you want. So it's doing the input adapting, it's doing the scaling out over a larger number of machines, it's doing some level of processing to produce then the set that you would consume for whatever you want later on. And all of that is sort of at your discretion. But that's the general pattern.
Thank you.
If I may add to that.
Sure.
That is a good example for event processing before you actually want to persist the data in a transactional storage. Imagine you have a data source like that which produces a lot of noisy data, a lot of noise which traditionally you need to store everything to be able to query that and figure out what's the noise and what do you want to keep. But what you actually want to do is do that in memory, in real time, before you go into transactional storage, before you persist the data, so that you're able to keep up with the data written in the first place. Use something like an in-memory event processing engine like Stream Insight, which is not transactional, so you can actually process 300,000 events per second. And then you figure out the remaining 5,000 you want to actually persist in a transactional storage. So that's kind of the edge processing example or area where we are also looking into.
Why don't we take one more and then?
Yeah, so I've kind of got the general pattern that you were saying is this whole MapReduce thing, reduce, reduce, reduce. But it seems like in this case we're going to be adding to the problem in that sense, because the more that we duplicate data, then the more data we're going to have to produce in the future and work through. So it kind of occurs to me that when we're dealing with petabytes of data, if I'm needing to query on to get a specific set of data back, if if I'm going to have to query across petabytes worth of data, that's going to take an awful long time. So it seems like that in order, rather than working with the master source, I'm going to have to reduce that further down. So rather than working with that master source, the question is, does my reduced set of data that I'm now working off of have all the data that I need to answer that question? And then it's going to go further down, and it's going to go further down because it's going to have that manageability of data. So my question is that since we have that kind of, we can see already that we're going to have this reduce, is my data there? How is Microsoft going to plan to sort of cover that within their product space so that I can manage all my various subsets of data? Or am I totally wrong on how I kind of see?
No, I think it's quite, I think you're right in terms of in the large. It's the dynamics, though, in the sense that if I've got 10 petabytes to process, and let's say that I could pretty much answer any question in 2 hours, okay? The point is that I never have to throw anything out. Any new question I get, I can produce a reduced set of data, order an hour, a couple of hours, that then I can do something. This whole data flow and data reduction sort of thing has been in use in the scientific space for a long, long time. And what's that? It's called graduate students. Yeah, we've got automated graduate students now.
Yeah, I agree, but I totally agree with you because it's a well-subscribed pattern, and as you say, it's used wherever. But the thing I'm thinking about, that's one question for, as you say, 2 hours. But if we talk about scale, then let's say I've got 1,000 questions which take 2 hours. I'm not going to, and basically I'm using the same set of data. I don't want to go through my 10 petabytes of data. I want to work on a reduced set. Which,
sure. So here's a couple ways that one thing we can do is actually piggyback and load a whole bunch of queries up and just run it across it all at once. We can, there's some smarts we can do there. The other thing we find is that you'll produce a reduced set that then will serve your analysis needs. So you produce a set and then you scratch your head on that for a month or so, and then refresh that at whatever rate. And then the third thing we can do is actually, you have to realize that in a lot of these cases, there's a stream of data that's coming in that is forming that large set. And what you do is you install dynamic things in there, and you can actually learn from the active event stream that's in real time, if you will. So the question, how is it feeding into the Microsoft product stream? This insight was a key part of what drove how we've architected Stream Insight. This insight is sort of why Eric is doing some of the things that he's doing. So you see the first elements of that starting to appear right now, and you'll see more from us going forward. So I've got to run. I thank you for your time. I hope something in here was useful to you.